Welcome to the demonstration corner. Today we're going to talk about a special sample cell using the Transient Line Source method for measuring polymers through the melt. But before we do, as custom here in the demonstration corner, we're going to turn the camera around and show you what's in our demonstration corner, talk a little bit about those instruments, and get to the demonstration. So this is our MP-1. This is what we'll be doing the testing, the sample setup and testing for measuring polymers from the melt on today. This is our advanced thermal conductivity, thermal diffusivity specific heat instrument covering several methods. The sample setup today is 2 transient plane source temperature platforms, which we'll talk a little bit about. This is what we describe as future-proofing your needs, as it's really has a wide, diverse range of methods and technology specifically designed to cover the widest range of application possible. To the left of us is our MP2. This is our portable or economic unit measuring thermal conductivity across transient plane source, transient hot wire, so using primary methods, making absolute measurements that follow the theory of these methods, just smaller ranges, but absolutely designed to measure accurate values over the range of the sensors and the application they're designed for. So measurement platform, that's our MP2. Our MPV is our mid-range measurement platform. It incorporates 2 primary methods, just like our other measurement platforms. Transient plane source for thermophysical properties of solids, pastes, and powders. Transient hot wire for thermophysical properties of liquids. So it's really the 2 primary methods that are used for measuring accurate thermophysical properties. Being our mid-range, it is our most popular model, as that mid-range does cover the bulk of the applications. But certainly when it comes to the MP-1, it is the application range that makes it popular, but also some of the added features such as wide range of temperature and multi-sample, etc., that really set it apart, in addition to its technical capability. So what we're going to talk today, talk about is polymers through melt. So this is a high-density polyethylene sample. We were approached, a little bit of background on this, we were approached in 2018 by several polymer companies, rather companies that are involved in thermal simulation software used in developing the parameters for injection molding. We're approached by a few of those companies to develop an improvement over the transient line source. So this is a needle. This is one of our needles. We make the transient line source. Following ASTM 5930, these pellets would be set up with a needle, and with temperature, they would be brought to a melt, and using pressure and temperature, the ideal situation would be this would be turned into a bulk solid, or rather from a solid to a solid, from a bulk solid to a solid, and all the air removed. That's actually quite challenging and quite messy and quite inconvenient. So that, if there's any porosity left in that sample setup, you end up with data that is suspect. So you end up with errors in your data. And of course, convenience is important, but accuracy is most critical when you're using data in simulation. So the solution we were asked to provide was addressing the poor performance due to the addition of porosity in the sample setup, as well as the inconvenience. And then the third was, we have a large amount of samples. Can you help us increase our throughput? So over a year, we developed a polymer melt cell specifically designed for the transient plane source, which is available in the MP-1, as well as the MPV and the MP-2. The added advantage of that method, in addition to the solution we're providing for the 3 issues just mentioned, is that it measures multi-property. So when you're using a transient line source, ASTM 5930, your output is only thermal conductivity. When you use transient line source. When you're using transient plane source, the output is thermal conductivity, thermal diffusivity, and specific heat. So we've addressed solving 3 main problems that we were asked to look at, as well as adding value that we get 3 properties. So those 3 properties can be quite critical for inputs into thermal simulation software. We'll show some sample setup, and on the with the cell, the samples we'll be setting up will be polycarbonate, and then we'll move over to the temperature platform and show you how those work together to develop easy setup and testing with temperature. Okay, so we're going to move over to the table here. This is a little snapshot of the sample cell kit. So to this side of us are examples of polymers that you can measure through the melt. So what we've designed is a sample cell that can be used from cryogenic all the way up to 300 or 400 Celsius. We've developed the necessary components to be able to achieve those ranges. And you can measure that from the melt, so from a high temperature to a low temperature, then back to a melt. So you can develop the two directions in temperature control. So depending on the temperature range you require, those components are available. So this is a melt cell that we use in our ovens. So it's not been optimized for the temperature platform. We'll show you that. So we're actually going to show you the exact same setup with a simple our polymer melt cell that's designed for the temperature platform, but this would be a melt cell designed for a standard furnace. So it's the setup exactly the same. So we're going to use our TPS sensor. This is 3.2 millimeters radius. You could also use one more size, which is 2 millimeters radius. The model on that is 21171. And this is our stand that we'll use to kind of pull it all together. So this is our bottom portion. So what we're going to do is we're going to introduce a layer of Kapton. So one of the main goals of this was to have polymers that never touch the sensors. So what that means is it's going through the melt. The polymer never touches, is never in direct contact with the sensor. Otherwise, it would destroy the sensor. It's very hard to remove those polymers after a melt if they're in direct contact with the sensor. Because we're able to see the contact resistance between the sensor and the sample, so as the heat travels through a layer of Kapton, which you'll see as we configure this, we can remove that portion of time. So anything we add, as long as it's a thin layer between the sensor and the sample, we can remove that effect. So the sample setup is one layer of Kapton. We use an O-ring to contain the sample as it's going through the melt. In this case, we have these discs that we've machined to polycarbonate. So this is the sample we're going to measure through the melt. And we have different O-rings of different types, so silicone and Teflon. And those all give us different temperature ranges or compatibility with the types of materials we're measuring. So it just depends. If you're measuring peak through the melt, you would use the Teflon O-ring. So it basically contains the sample, and you'll see as we configure this, it contains the sample in contact with the sample, in contact with the sensor rather. The next step is another layer of Kapton. So that's our sandwich for the bottom half. So we're symmetrically configuring the sample to the sensor. So this is our top portion of the sample cell. So I'll just clamp it gently, rather a few threads. And then we're going to insert the sensor. And what I'm going to do is just sort of show you what the view looks like. Hopefully you can see that. So that sensor is centered in the middle of that sample. And then we're going to use our jig to configure the rest of it. Actually, no, we can put the next steps in. So the next step is another layer of Kapton. So we're creating a mirror of what was on the bottom, an O-ring. Our sample, and then another layer of Kapton. So that sandwich is 2 contained discs of the sample with 2 layers of Kapton on each side. This is our top portion that will push down and bring it all together. And then we use springs. So each of these springs has different pressure. So you can have 3. There's actually a third one, and they have different forces. So depending on the viscosity of your sample at the melt, if it has very low flowability, maybe use more force versus less force. So we will assemble, we'll screw this together. And that's our we just use that to squeeze it. Actually, we'll do a couple threads first. And we can squeeze that, and that compresses the springs. We can make final test setup. So that's your assembled polymer melt cell all together. So we can bring this over to the temperature platform and run and set up our temperature step. So just bring it over. This side of me, please. This side of me, please. So this is our temperature platform. So this has a built-in range of 0 to 300. You can extend this down to -45 or -160. So once we assemble that, these 4 contacts make electrical contact with the sensor. And that's the setup. So we'll use the top lid. This closes the temperature, so the heating portion of the temperature platform. It completes the heating step, and then the cold completes this lid completes the cold. So you have a heated cell inside a cold cell, and that gives you very good control of temperature. And then we put this on. This has a switch inside that makes the it's a safety so that you can't burn yourself. That's ready to schedule a measurement in the software. So we'll go over to the software and schedule that. We have 2 set up here to just show you that if you want it to run 2 samples at different temperatures, you could actually add up to 4 of these. That would give you flexibility on running samples, whether they're the melt. Of course, with melt, you typically are measuring them all with a temperature range. That gives you flexibility to do that. So I'm going to share my desktop. So before I do that, this method was presented. I thought I'd share this little presentation. This was presented at Moldflow 2019, which is a conference. They shared the specifications on the transient plane source method. Key that it actually gives you the output of thermal conductivity, thermal diffusivity, and specific heat. So it's a big upgrade in terms of if you're measuring a polymer through a melt. You can see we worked together to develop this arrangement of sample between springs that keeps a constant pressure between the sample and the sensor, even as it's going through the melt. And most importantly, that it's clean post measurement. You're not destroying sensors. So what you can see from this slide on the right is that these, once we remove the sensor, those sample pieces are clean. The other configuration, other than the temperature platform, which is 1 sample per temperature platform, so you can have 2 different samples going in 2 different temperatures, is you could put several samples in the same oven. So this is the MP-1 comes with a 4-channel switch. So you could actually set up 4 samples within the same temperature and run and go to a temperature and run all 4 samples, or 2 or 3, and then go to another temperature and run that many. So that automation of the switch, which allows you to connect multiple devices to the same controller, is quite an advantage, whether it's for running single temperature profiles or temperature profiles across multiple samples. And you can see here the configuration of different types of gasket material that are used to contain the sample. So for our sample setup, you can see here the MP-1 detects the 2 temperature platforms as well as a room temperature sample holder. We're going to use this particular temperature platform. This is polycarbonate. The thickness of that polycarbonate is 3.2 millimeters. The radius for this size of polymer melt cell is fixed at 9 millimeters radius. The thickness can change. So those springs allow a certain amount of flexibility in sample thickness. These in particular are 3.2 millimeters. So we've already done an electrical check on the sensor. So proceed to the schedule portion. So here we can say, I want to go from 0 degrees, maybe 20 is more realistic, to 300, and by, let's say, 25 and back. So that'll develop a schedule based off of those increments of temperature that we're looking to achieve. 25 milliwatts, and that's a 5-second test. And what it'll do is it'll run 5 measurements at each temperature step with a 10-minute delay. So once we add that to the schedule, you'll see that it'll build the schedule. So from 20 up to 300, then you'll see it go back down. So we'll actually have data as it's going through solid to liquid, and then as it's going from 300 down, you'll see it go from solid, or rather from liquid to solid, back down to room temperature. So it's quite convenient. Click start, and now it'll set the temperature platform to the first temperature step of 25 degrees and proceed through the measurement. So once that's done, your data would look like this. So this is polycarbonate that's been measured from 25 degrees up to 300. Rather, it's been heated to 300 and tested from 300 down to 25 degrees. You can see where it transitions from liquid back to a solid. You can see that the melt, the effects of the melt on the thermal conductivity. And here's ABS. So this can be used up to 400 degrees with the oven that will go up to 400 degrees as well. So it does show you the use of this method for measuring melt. And then you can see the sample, what it looks like after you've finished your measurement. So I'll share the camera here and show this in a moment, what these look like once you can just pop them out nice and clean. So that kind of concludes. So I'll turn the camera back to this. And once you remove them, you can see the contact is so good that it even leaves the impression of the sensor. It might be hard to see. That's why I was showing you the website screen, is because you can see a little bit better that you have such good contact. So that concludes the solution we provided for really an improved method of measuring polymers through the melt over ASTM 5930 due to the effects of porosity, generating bad data, the inconvenience of dealing with polymers through the melt, and the third is basically giving multiple properties. And then you benefit from the speed of measurement by being able to test multiple temperature profiles or one profile with multiple samples using the TPS switch. So hopefully that was helpful. If you have any questions on that, we're happy to share this PowerPoint or get in contact with us, and we'll provide you more information. All right, thanks so much. Bye-bye.